Well, friends, the last lecture was devoted to application of t-test, and this lecture will focus on f-test. F-test as part of analysis of variance. As such, F ratio is used for testing null hypothesis regarding equality of variances or the variance of the population is a particular quantity. Like null hypothesis H0 can be that sigma square of the population from which a sample is drawn is this. It can also be used for comparing variances of two different populations or two subgroups within a population. Analysis of variance is a complete field of study in statistics, and we are not going to discuss everything of analysis of variance. It is not possible in one lecture, but we will show how in certain situations application of analysis of variance helps us in causal analysis in sociological or empirical research. So, we begin with what is ANOVA. ANOVA is abbreviation for analysis of variance. It is part of causal analysis when the dependent variable is a numeric variable and the independent variable is qualitative. And therefore, this application of ANOVA differs from analysis using multiple regression analysis. In multiple regression analysis, most of the time we assume that our dependent variable is numeric. Independent variables are mostly numeric, but there may be some qualitative variables also for which dummies are used. In case the dependent variable is categorical or qualitative, then we use probit and logic transforms of the dependent variable. ANOVA is used when the dependent variable is numeric, dependent variable is measured at least on interval scale. If not on ratio scale, it is measured on interval scale, and the independent variables are qualitative or categorical. For example, we may discuss do different regions in the country, you divide the whole country into 4 or 5 major regions according to some criterion, and then ask the question whether the different regions in the country differ in terms of industrialization or per capita income or fertility or migration rate or crime rate, suicide rate, or in happiness score or in anything. So, dependent variable is quantitative. Its scores or measures something measured on a scientific scale, usually on interval scale. If the number of groups to be compared is only 2, then as we have seen in t-test, you can use t-test for comparing means or proportions of 2 groups only. You can use t test or z test. But when you are simultaneously comparing 3 or more groups, then t test cannot be applied. Then we go for f test, and comparison of means of some variable between 3 or more groups is done by applying the principles of analysis of variance or ANOVA. In ANOVA, however, you can also use t test as part of causal analysis when, after establishing that the different groups, 3 or more groups, differ from each other significantly, their means differ from each other significantly, you want to know in which pairs of groups there are significant differences. You may have 4 groups. 5 regions of India may differ with respect to something, but it does not mean that if you take them pairwise 5, C2 or 10, there are 10 pairs of 5 regions, then there are significant differences in all the 10 pairs. This may not happen. So, which are the groups which differ significantly from each other? That pairwise analysis can be done by using t test. By using f test, I am sorry, by using f test. Like t or like z, f also has a probability density function. Probability f for variable value x is defined as this. Here there are 2 more terms d1 and d2. They are called degrees of freedom. So, there are 2 terms d1 and d2 indicating degrees of freedom in f ratio or f distribution. The degrees of freedom concept is not new. You had degrees of freedom in chi-square. In contingency table, this was r minus 1 into c minus 1. In t test, for testing the null hypothesis mu equal to mu 0, you had n minus 1 degrees of freedom for t. For comparing 2 means, you had degrees of freedom n1 plus n2 minus 2, where n1 and 2 are sample sizes from the 2 groups. Likewise, here you have a concept of degrees of freedom, but there are 2 terms indicating degrees of freedom. Actually, this f distribution is a distribution of ratios of 2 variances. You may call them sigma 1 square and sigma 2 square. So, probability density function f x d1 d2 shows the probability density function of sigma 1 square divided by sigma 2 square, and d1 is the degrees of freedom of the numerator sigma 1 square, and d2 is the degrees of freedom of the denominator, which is sigma 2 square. So, there are 2 degrees of freedom associated with f. More precisely, you can write f x d1 d2 into dx equal to this whole thing into dx, and this is written as square root of d1 x raised to power d1 into d2 raised to power d2 divided by d1 x plus d2 raised to power d1 plus d2 and divided by x beta d1 by 2 comma d2 by 2, or it is also written as 1 upon beta d1 by 2 comma d2 by 2 d1 by d2 raised to power d1 by 2 and x raised to power d1 by 2 minus 1 in bracket 1 plus d1 upon d2 x raised to power minus d1 plus d2 by 2. Students of sociology are often phobic of statistical application. Do not worry about this, you are not going to use this complicated or this difficult formula, you will get a definite value of f. Computer G will give you a definite value of f, and you will calculate your own f as calculated t or calculated chi square and compare it with tabulated value of f. So, your task is simple, and calculations using this complicated looking distribution will be done by computer for you. Nobody does analysis of variance manually these days. As far as graphical picture of f is concerned, I think in some context once I said that all distributions tend to behave like a normal distribution when degrees of freedom is large. Same is the case with f ratio. Here 5 different distributions, all f distribution. F is a family of distribution, and a particular f is defined on the basis of two things, d1 and d2, degrees of freedom of the variance in the numerator and degrees of freedom of the variance in the denominator. When d1 is 1 and d2 is also 1, you have f distribution like this. To some extent it looks like a negative exponential distribution. When degrees of freedom d1 is 2, d2 is 1, then you have this distribution. It also looks like negative exponential distribution, but in place of starting from here, it starts from here. Okay. When d1 is 5 and d2 is 2, then it looks like this distribution. When d1 is 10, means degrees of freedom has increased, but d2 is 1, then the distribution looks like this green one, this. These distributions look like chi square and they are positively skewed distributions. But when degrees of freedom is large, numerator is based on degrees of freedom 100, denominator is also based on degrees of freedom 100, then you have a distribution like this, a symmetrical. It is also positively skewed slightly, but it is more like a normal distribution. So, as degrees of freedom increase, your f distribution tends to behave like a normal distribution, and you can use values of z for your analysis of variance purposes also. Example, we begin with an example of a situation in which one way, it is called one way, simple analysis of variance is used. It is simple one way because there is one dependent variable and there is one independent variable. The example is this, that there are 30 students who are selected to examine the impact of 3 different teaching methods. 10 are randomly allotted to each group. You can adopt other techniques of allotting to different groups also, matching, or there are many other ways of doing this. Suppose we allot 10 students to each group randomly, and then different methods are tried in different groups, different teaching methods are tried in different groups. At the end of the semester, the following results are obtained. I will show you that with the help of a table. So, you have data on all 30 students divided into 3 groups, on which 3 different teaching methods are used, and they are given marks in 100. Can we derive any inference on the basis of differences in means if the data are cross classified according to groups. So, like this. There are 10 students in this group, 10 students in this group, 10 students in this group, and they are randomly assigned. When a large number of subjects are randomly assigned to 3 groups or 4 groups, we assume that there are no basic socio-economic or other differences among students which can interfere or interact with teaching methods. So, if we now find differences among means of students in these categories, we assume that these differences are due to 3 different teaching methods used. Maybe some method is better than other methods and produces better results. Among students where teaching method 1 is used or 2 is used or 3 is used, there are some in which students will perform better than in groups where other teaching methods are tried. So, at the end of the experiment, 10 students in group 1 get these marks 78, 89, 50, 37 and so on. The mean of this group is 59. In second group, teaching method 2 is used, and the marks of the students at the end of the experiment are 78, 65, 66 and so on. The average of them is 64.6. In third group, where teaching method third is tried, their marks are 30, 100, 58, 70 and so on. And here the arithmetic mean of the group is 49.9. Now, we have to draw inference regarding, it appears that teaching method 2 is better and teaching method 3 is worse if you go by mean only, and that is one unitary measure or performance in a set of students which can be compared with other groups. So, when you use arithmetic mean, you can say that teaching method 2 is better. It is the data when different drugs are tested or different seeds or fertilizers or extension programs are tested is exactly the same. And the biggest users of F ratios or analysis of variance in surveys are sociologists who go for large scale surveys. So, for analysis of data in national sample survey, surveys conducted by applied economic research or IIPS, they would require use of F ratios for causal analysis. I was reading a paper by someone on vitamin A deficiency, and in the paper vitamin A deficiency was explained in terms of a number of socio-economic variables and gender. So, similar causal analysis can be done by using ANOVA, but that requires, when you are dealing with so many variables, socio-economic and gender type, then we require a much sophisticated analysis of variance than we are showing here. This is just an introductory lecture on ANOVA. This is not what we actually will do, but in many situations when you have one dependent variable and one independent variable, this much of analysis of variance is okay. This will essentially help you to understand the concept of F and what is the use of applying ANOVA. The difficulties in comparing means is that on the basis of means, certainly teaching method 2 seems to be the best, as its mean 64.6 is higher than of teaching method group 1 and group 3. Their means are lower, 59.1 and 49.9. If the data come from census, again even small differences between groups are meaningful. But the problem with sample or experimental studies is that there are a lot of variation within the group, which are sort of or which can be called variations due to sampling fluctuations. Okay. Not all students in group 2 have done equally well. So, there are variations within. There are many students in group 1 and group 3 which are better than many students of group 2. If another researcher conducts the same study, shall we get the similar results? There is no guarantee, because values vary both between the groups as well as within the groups. They are subjected to sampling fluctuations. So, we have to make a meaningful statement about differences in means. We have to estimate the impact of sampling fluctuations on differences in means. Simple differences in means, in case the data have come from sampling, would not be producing any valid and reliable result. Suppose the results are as shown here. This is a hypothetical situation. The real situation would be like this only. This is the realistic situation. Here I am making a hypothetical situation. What is unique about it? That means are same, 59.1, 64.6, 49.9, and all the subjects in one group have the same value, 59.1, 59.1. It is in this situation we say that there are no variations within the group. Now, these data suggest that you can assign more meaning to differences in means, because within differences are absent. It appears, to be more exact, more valid, we still have to apply F test and let us see what happens. But in case of these unique data, we can be more sure that group 2 is better than group 1 and group 1 is better than group 3, because there are no differences within. On the other hand, you may also have a situation in which means of 3 groups are same, 50, 50, 50, but there are lot of variations within. In the first group, you have one subject who secures 0 and another subject who secures 100. There is a range from 0 to 100. In the second group, variations are relatively smaller. The lowest value is 10, the highest value is 90. In the third group, lowest value is 8 and the highest value is 90, and there are variations as in the other two groups. It is difficult to predict means or at least more difficult to predict means of these 3 different groups. It is more difficult than in the previous situation. In the previous situation, there are no variations within, and therefore, one can say that if you add 1 or 2 or 5 more respondents to each group, or you take another sample, perhaps the situation would not change. But in this case, you cannot say that there are no differences between groups. The situation might change if you draw another sample of students from this population, okay, or you repeat the experiment. This is a more realistic situation, however. that there are variations between 50, 60, 40, arithmetic means are 50, 60, 40, and there are also variations within. Okay. Now, the example which we have selected for solving the problem of removing the effect of sampling fluctuations from differences in group means is like that only, that there are differences within as well as between. So, there are two types of differences that we find in dealing with ANOVA cases: within each group, between each group, calculated on the basis of mean. They can be measured through variability or sum of squares divided by the degrees of freedom to have an estimate of variance in the dependent variable in the population. Now, you can make estimates of variance in the population by using two types of data, or rather three types of data. One, the whole data set combining all three groups. Second, by taking means of the groups, and third, by taking within differences, differences within each group. This analysis of variance is based on comparison between estimates of variance based on variations between groups and within groups. Differences between means, from differences of means you calculate sum of square, which will be called between, because differences in means show the differences between different groups, and the other one within, a measure of differences or sum of squares of differences of subject values from means of the respective groups, will be an indicator of sum of square within. When they are divided by appropriate degrees of freedom, then you have between and within estimates of variance of population, and another estimate of variance of population would come from calculating sum of square for all 30 subjects irrespective of the group. The ratio of variances, estimates of variances, what are we estimating? We are estimating variance of the population by using sum of square of the entire sample, sum of squares of different groups, between groups, and sum of squares for within. It is found that the ratio of estimates of population computed from between groups and between groups in the numerator, and estimate of population variance using sum of squares within, that follows an F distribution. Tables of F distribution for different degrees of freedom are available. They will look like table for T distribution, except that in T distribution there is only one degree of freedom, but here you have two different degrees of freedom, one associated with numerator, another associated with denominator. And if this is the F distribution, by fixing p value or alpha or type 1 error, you can find out a value of f beyond which critical region lies for degrees of freedom d1 and d2. This is the distribution, and you fix a value of f, that if my calculated value of f is less than this, then I will accept the null hypothesis. But in null hypothesis, that the variances, estimates of variances on the basis of between and within are same. So, in general, the model or the data set for which analysis of variance is used would look like this. Now, interestingly, the model of the ANOVA is expressed not in terms of variances, but like this. This is that any this is a data matrix. The first subscript shows this x11, x12, x13. First subscript shows the observation on first subject, and second subscript shows the group. So, x11 means first subject of group 1, first subject of group 2, first subject of group 3 is shown by x13. Likewise, 21, 22, 23. In general, xi1 means ith subject in group 1, ith subject xi2, ith subject in group 2, i3 ith subject of group 3. If in all you have 10 subjects in each group, then 10 1, 10 2, 10 3. The model is that xij is mu plus alpha j plus eij. Xij is the score of ith subject in jth group. Ith subject in jth group, like I1, ith subject of group 1, ith subject of group 2 is xi2, ith subject of group 3 is xi3. So, ith subject of group J may be 1, 2 or 3 is mu plus alpha j plus eij. Here mu is the overall score, some mean score overall. Alpha j is effect of jth group and eij is a random error with a normal distribution with mean 0 and a fixed variance sigma square e. What is of greater interest is alpha j, is the effect of belongingness to jth group important, to what extent? Is first group important, is second group important, is third group important? And always in empirical situation there will be some sampling fluctuations. Eij stands for difference between empirical value of ith subject in jth group xij and mu plus alpha j, which is what we expect. Mu is overall and alpha j is the effect of jth group. So, what we will expect from any particular subject in jth group. The null hypothesis is stated as follows, that alpha 1 equal to alpha 2 equal to alpha 3 means group effects are similar. Alternative hypothesis would be that at least 2 of the groups differ. If there are 4 groups, the null hypothesis would be alpha 1 equal to alpha 2 equal to alpha 3 equal to alpha 4. And alternative hypothesis would be that at least any 2 of 4 groups differ from each other. Note that although the null hypothesis is about means, the test is the ratios of 2 estimates of population variance, one based on sum of squares between groups and second based on sum of square within, which is also called the error sum of square, because it is due to sampling fluctuations and not due to effects of the group. Why does this happen? Because these alpha 1, alpha 2, alpha 3 are estimated by method of least square, and it can be shown that the estimate of variance of population based on between groups will be equal to the true estimate of population variance only if alpha 1 equal to alpha 2 equal to alpha 3, otherwise it will be higher and higher than a threshold level. That threshold level would come from study of F distribution. So, you have 3 sum of squares, a total sum of square as the sum of squares of differences from grand mean for all the observations, and degrees of freedom would be sample size, total sample size combining the 3 groups minus 1. Between sum of squares will be the sum of squares of differences of group means from the grand mean, each multiplied by number of observations in that group. The degrees of freedom for 3 groups will be 3 minus 1 or 2. If there are 4 groups, degrees of freedom will be 3. If there are 5 groups, degrees of freedom will be 5 minus 1, 4. Then within sum of squares, as the sum of squares of differences of all values from their group mean, not from overall. From overall mean is this total sum of square, from mean of the respective group, that is within sum of square, and algebraically it can be shown that total sum of square is between sum of square plus within sum of square. What alpha is? This between sum of square divided by degrees of freedom for between, which will be 3 minus 1 or 2, divided by within sum of square divided by its degrees of freedom, which will be degrees of freedom of the total minus degrees of freedom of between sum of square. That means, n minus 1 minus 3 minus 1, like that. So, this slide shows the degrees of freedom for total sum of square n minus 1, for between sum of square k minus 1, k is the number of groups, and for within sum of square difference between the two, and that becomes n minus k. As the number of groups increases, this degrees of freedom of between sum of square will increase, and degrees of freedom of within sum of square will decrease. So, as I have said, we get 3 estimates of variance, one by dividing total sum of square by its degrees of freedom, one by dividing between sum of square by its degrees of freedom, one by dividing within sum of square by its degrees of freedom, and the expected value of the first and the third. First total sum of square and third within is same as the variance of the population. It can be shown. It has been mathematically or algebraically shown. The expected value of the second between sum of square is equal to or more than the variance of the population. It is equal when the null hypothesis that alpha 1 is alpha 2 is alpha 3, that is true. When that is not true, when at least 2 groups differ, then the between sum of square will overestimate, variance estimate based on between sum of square will overestimate the variance of the population. Thus, the ratio between the second and the third estimate is a test of the null hypothesis. Null hypothesis is stated in terms of comparison of means, and the test statistic that we use for this is F, which is ratio of 2 variances. If null hypothesis is rejected, at least 2 groups differ. The assumption, there are like any other technique, ANOVA is also based on certain assumptions, and they are that all the k populations from which k samples are drawn have a common variance. This is called homoscedasticity. All the observations are independent, that is, the method of teaching applied to one group has absolutely no effect on the observations in the other two groups. In other two groups, different teaching methods have been used, which are unrelated to teaching method in the first group. F ratios are based on a linear model, although F ratios are ratios, but the model is linear because this is mu I j equal to mu plus alpha j plus E I j, that is a linear model. E I j is the random term, it shows a normal distribution with mean 0 and a fixed variance sigma square E. If this variance is not fixed, then you are having the problem of heteroscedasticity, check it, make corrections and then apply analysis of variance. Some modified analysis of variance will be applied. In x I j equal to mu j plus E I j, all group effects are estimated by using method of least square, the same method which is used in estimating parameters of the regression model, method of least square, and are equal to the difference between group mean and grand mean. Okay. The results of ANOVA, the computer output in analysis of variance will look like this. These results of ANOVA, in the first column you have between groups, within groups and total. This is total sum of square. This is sum of square between groups. This is within groups. If you add the two, you will get this 1103.267 plus 13542.200 is 14645.467. So, essentially you have broken down this total sum of square into two parts, sum of square due to between and sum of square due to within. Degrees of freedom of between when number of groups is 3 is 2. Degrees of freedom in case you have 3 groups each of size 10. So, number of subjects in the experiment, total number of subjects is 30. So, the degrees of freedom is 29 and the difference between 29 and 2 is 27. This is the degrees of freedom of within groups. Now, to arrive at estimate of population variance, these sum of squares have to be divided by degrees of freedom. So, 1103.267 divided by 2, you get 551.633. 13,542.2 divided by 27, you get 501.563. You can divide this by this also and you will get an estimate of variance of population, but usually that is not written because that does not serve any purpose. We want to compare these two. If alpha 1 is actually equal to alpha 2 and that is equal to alpha 3, if the means of the 3 groups are really same, then this as well as this will be equal to estimate of population variance. But in reality, for your empirical data, this value will be more than this, because this value overestimates the population variance. This will be equal to variance of the population only when the groups have the same effects. So, now we use F ratio, divide this 551.633 by 501.563, we get 1.1. In F distribution with degrees of freedom 2 and 27, numerator degrees of freedom is 2, denominator is 27. In F distribution with degrees of freedom 2 and 27, 1.100 is that value of F beyond which, means on the right hand side of which area 0.347 lies, which is much higher than 0.05 or area of the critical region that you normally fix 0.05, 0.01, 0.001. So, that means your f point, this calculated f point falls in the acceptance region, and that means null hypothesis is not rejected. Null hypothesis was that means of the three groups are same. So, although they look different, but the differences between groups do not carry any statistical significance. The reason is that there are variations within groups also, which reflect that there are high sampling fluctuations, and it is by chance that you are getting differences between groups. If you conduct another study using the same methodology, you may not find differences between teaching method 1, teaching method 2, teaching method 3. Like any other statistic, F ratio or analysis of variance also has some limitations. There may be 2 or more factors affecting scores. Here we have studied effect of only one thing, teaching methods. Suppose you hypothesize that teaching methods make a difference and gender of subjects also makes a difference, then there are 2 causes. But that is not much big a problem, and in this case you will require between sum of squares separately for teaching methods and gender. Degrees of freedom of gender will be 2 minus 1 or 1, and degrees of freedom of within will be further reduced, because degrees of freedom of within will be total degrees of freedom n minus 1, like 30 minus 1 minus between teaching methods. So, 3 minus 1 minus gender groups. So, 2 minus 1, degrees of freedom of within will be reduced. Sum of square will also be reduced, because sum of square for gender would be total. Sum of square for gender will be calculated as for teaching methods, and within sum of square will now be total sum of square minus sum of square for teaching methods minus sum of square for males and females. Simple. And then 2 F ratios will be required, one for teaching methods and another for gender, and both of them may be significant, both of them may be insignificant, one may be insignificant, another may be significant, that depends. So, the example of ANOVA that we gave was a one-way ANOVA, in which there is one independent variable. If there are 2 independent variables, you have two-way ANOVA. So, that limitation can however be handled easily. The teaching methods may actually differ, but since the composition of subjects in different groups in terms of gender, urban, rural, learning abilities, etc., may not be same, we do not find the difference. One reason why we do not find the difference is that maybe if those exposed to better teaching methods are actually inferior, and those who are exposed to poor teaching methods are superior. So, the effects get neutralized, and therefore, allotment of subjects to 3 groups is a very important exercise. It has to be done in a manner that there are minimum of differences among subjects in 3 groups. Sometimes we may find the difference, but it may not be due to teaching methods, but due to other reasons, as the composition of subjects is not same. Yes. Similar point as this, that the effects of teaching methods and background of respondents are confounded. heteroscedasticity when the variances of the groups are not same, and then also we have problem in applying ANOVA. Small differences, however, do not matter, and it is more complicated than other techniques. It takes time to produce results. This is based on experiment. So, the options are, first of all, you learn from the review of literature whether you need to use one way ANOVA or two way, or consider two or more assignable causes. As far as possible, use sufficiently large samples with randomization. So, you take a large number of respondents and allot to different experimental groups through randomization. By law of large number, we assume then the background characteristics of different groups will be similar, or you can use matching. If you think that gender matters, number of males and number of females in all the groups should be similar. If you think that age group matters, then number of subjects belonging to different age groups in the three groups according to teaching methods should be similar, or you go for panel data or longitudinal study, means time series. After you have found that F is significant, you can do pairwise analysis. Even otherwise, even if F ratio is insignificant, you can do pairwise analysis, and that but it makes more sense when you find that F is significant. From which groups is that significant difference coming? So, you use T. T is mean of the first group. This is for comparing first and second, mean of the first group minus mean of the second group, divided by S, standard deviation, and in bracket 1 upon n 1 plus 1 upon n 2. Remember, this was also the formula of T. There is this 1 by 2 over this bracket 1 by n 1 plus 1 by n 2. This is the same formula which we use for comparison of means between two groups. Then what is the difference in T, group wise T and T of ANOVA? The difference lies here, S. This S is the mean square error. This is obtained by dividing sum of square for within by degrees of freedom of within, and it is found that T defined in this way as part of analysis of variance is more powerful a test than simple T. This is an example of how we calculate T. This table shows the results of analysis of variance, one way analysis of variance in notations. This shows that if there are 4 groups, these are confidence intervals of means of different groups. If you show them in the form of a graph like this, that also gives a picture what are possible differences between the group. Now, toward the end, I must say that the issue of type 1 error is especially significant when you are doing pairwise analysis in ANOVA. Normally, type 1 is fixed at 0.05 or 0.01. You are dealing with 3 groups. Imagine that type 1 error for each comparison. There are 3 groups and 3 pairs, 1 and 2, 1 and 3, 2 and 3. So, if you fix probability of type 1 error in each pairwise comparison at 0.05, then the probability that you do not make type 1 error in any is this 0.857, and therefore, the probability of committing type 1 error in the entire analysis would be 1 minus 0.857 equal to 0.143, which is not 0.05. So, fixing alpha at 0.05 means that alpha for the entire sample will be more than 0.05, it will be 0.143. I calculated that if we want to achieve 0.05 for the entire sample, what should be the type 1 error for pairwise comparison, and that comes out to be 0.016, because 1 minus 0.016 raised to power 3, that there is no type 1 error in testing null hypothesis in first pairwise comparison and in second comparison and in third comparison by using multiplicative rule of probability will be 1 minus 0.016 whole thing raised to power 3, and it will be 0.95. So, the probability of making type 1 error for the entire data, for the entire sample would be 1 minus 0.95 or 0.05. So, remember that if you are making, if you have 3 groups and you fix alpha at 0.05 in each pairwise comparison, then the alpha for the entire set is 0.143. If you want to achieve 0.05 for overall, then pairwise alpha should be 0.016. So, this is what analysis of variance is. If you may have 3 groups, you may have 4 groups, also you may have 2 assignable causes. Teaching method may be one factor in differences in scores, other factors may be gender, urban rural background, caste, religion, IQ, and in that case you will make a model in which mu plus alpha j plus beta something plus gamma something, there will be effects of all the groups. There will be effects of teaching method, there will be effects of gender, effects of urban rural residents and so on. This is called 2-way or 3-way, depending on number of causes, 2-way, 3-way, 4-way analysis. The logic is same. There is also sometime a joint effect of 2 variables, and that joint effect is called interaction. There are ways of handling interaction also, but all these things will take us to a more advanced level of analysis of variance. This was only an introductory lecture. I suppose the basic idea of doing analysis of variance and testing null hypothesis regarding differences of means between 3 or more groups is now clear to you. This is what analysis of variance means. Thank you very much.